In this video, we'll continue to think about linear regression and, in particular, examine ways to use categorical predictor variables and multiple predictor variables simultaneously. In the previous videos, we considered the percent of deaths in each country that are caused by indoor air pollution and explored some variables that could be related to this percentage. We started by looking at the percent of the population with access to clean cooking fuel as a predictor. We used linear regression to create a model to predict the values of the outcome variable and created a general model that took into account the error in our predictions, using the general idea that the data values could be expressed as the predicted values plus the error terms, or residuals. We looked at several other predictor variables, but, like this one, they were all numerical variables. However, it is also possible to use a categorical variable as a predictor. For example, we could look at whether or not the majority of the population lives in urban areas as a predictor of the percent of deaths caused by indoor air pollution. In this graph, the green dots indicate a country in which less than 50% of the population lives in urban areas, and the orange dots indicate a country in which at least 50% of the population lives in urban areas. Then we could separate our data points into these two groups. In order to use linear regression with these categorical data, we treat this categorical variable as an indicator variable by using 0 to represent less than 50% of the population living in urban areas, and 1 representing at least 50% of the population living in urban areas. Then, to construct a model, we just use the means in each of the two levels of the variable. The resulting linear model will predict that the outcome for each level of the indicator variable is equal to the mean, and the general model will incorporate the error term to represent the fact that the individual data points can vary from the mean. Now, not only can we create models using categorical variables, but we can create models that incorporate multiple predictor variables too. In these videos, we have been considering the percent of deaths caused by indoor air pollution as our outcome variable, and we've considered several predictor variables. The percent of the population with access to clean cooking fuel had a linear relationship and a large coefficient of determination. But since r squared is less than 1, this variable doesn't, on its own, explain all of the variation in the outcome variable, so it might be beneficial to consider additional predictor variables. The percent of the population living below the poverty line also had a linear relationship and a moderate coefficient of determination. We also looked at the per capita gross domestic product. This appeared to have a strong relationship with the outcome variable, but the relationship was nonlinear. It is possible to transform this variable to make the relationship linear, but that is a topic for another video. So for now, we won't use this variable in our model. Finally, we looked at whether the majority of the population lives in urban areas. This was a categorical variable, but the coefficient of determination was moderate, and it's still possible to use it in our model. As before, actually creating the model requires some sophisticated software. Now, if we label our three predictor variables as CCF, BPL, and urban, and our outcome variable as IAP, then the model we get is shown here. This model says to predict the percent of deaths caused by indoor air pollution in a country, you would multiply the percent of the population with access to clean cooking fuel by negative 0.097, then add the percent of the population living below the poverty line multiplied by 0.034, and then subtract 1.495 times the indicator variable of the majority of the population living in urban areas, and then add 10.726. This is an example of a multiple regression model. Now that we have our model, we can think about how well it predicts the data. The coefficient of determination for this model is 0.905, which means that 90.5% of the variation in percent deaths caused by indoor air pollution can be explained by a combination of these three variables. Let's compare this to our old model, which had a coefficient of determination of 0.872. This meant that 87.2% of the variation in percent deaths caused by indoor air pollution can be explained by the percent of the population with access to clean cooking fuel. So incorporating these two additional variables into our model did improve the accuracy of our predictions, but this increase wasn't particularly dramatic. This might be a bit surprising, because both of the additional two variables were added to our model and they themselves had moderately large coefficients of determination. Another thing you might have noticed is that the coefficient for the clean cooking fuel variable in our old model was much larger than its coefficient in the new model. The issue is that our three predictor variables aren't all providing independent pieces of information. Instead, we're seeing the effects of multicollinearity, which means that two or more of the predictor variables are correlated. For example, we could examine whether countries with low access to clean cooking fuel might also have a large percentage of people who live below the poverty line. If we examine the scatter plot, there appears to be a linear relationship between these two predictor variables. And it turns out that the correlation between them is negative 0.623. So these two predictor variables do appear to be correlated. So does this mean that there's something wrong with our model? Or that we didn't construct the most accurate model? Not necessarily. It's highly likely that any two predictor variables you select will be correlated to some extent. You might be tempted to just use a full model, which includes all of the available predictor variables. But this model might include predictor variables that don't have a high predictive relationship with the outcome variable. Instead, the goal is to create a parsimonious model, which means that it includes only the most important predictor variables. There are multiple methods for generating a parsimonious model, but we'll examine those in another video. Now, let's take a look back at what we've seen in this video. In this video, we explore the idea of multiple regression, where we examined a linear association between the outcome variable and multiple predictor variables. We saw that the predictor variables can be categorical. The categorical variable we looked at here was binary, but you can also use non-binary categorical variables in the model. Our goal was to incorporate additional predictors into the model to account for variation in the outcome variable, that is, to increase R-squared. We constructed a model to do this prediction by using a linear combination of the available predictor variables. And it turns out that we needed to be careful about which predictors we included in this model, and as we built and interpreted the model, we needed to consider the effects of multicollinearity.